Hey, I'm Lyle Burgoon. Thank you for looking at my poster. It's called Strengthen Teams, AI Human Hybrid Intelligence, Define Approaches, and Improve Risk Assessment. And what I'm trying to do is I want to get people a little bit more familiar with the idea of human AI hybrid intelligence or AI human hybrid teams and how they can tend to work better than ensemble models or other types of artificial intelligence schemes, and it's based a lot on what's called Kasparovs Law. Kasparov, the chess grandmaster, noticed several years ago that if you take a bunch of computers and you have them play chess against humans, humans tend to win. If you were to take, though, a person who's an average chess player who has a really great knowledge of how those algorithms are working, they can team together and they can tend to do really well against, even chess grandmasters. But if you take someone who's a great chess player and you pair them up with the computer algorithms, they don't tend to do well unless they actually understand how those computer algorithms work. So, one of the observations that Kasparov made was that ensemble models don't necessarily work very well, and we've seen this, in practice as well. And in my practice, and other consultants have reported the same. Ensemble models are great ways of bringing computational models, maybe QSAR models that are all focused on the same idea or same endpoint, bring them together, and then you kind of get, hopefully the models balancing each other out, and you may end up with a better prediction overall than you would from any one of those models. And that's very similar to the idea of in science, where you're going to replicate a study many, many, many times. Eventually, what you're going to have is you're going to tend to converge towards the mean as you increase the number of replications out to infinity. We would hope to see something very similar with ensemble models. However, ensemble models also, they are like any other kind of sampling technique from a population distribution. Their performance is going to tend towards the mean only as we go out towards an infinite number of models. How many models does it take for us to actually get to the mean? It's unclear. If we had lots of really poor models going into the ensemble and we had a couple really good ones, the poor ones are going to tend to bring the performance down. So although ensembles are great in theory, we may not be at a point where we have enough different models all looking at the same thing for them to be as great as we hope they can be. Part of this is also because ensembles can't really weigh the strengths and weaknesses of each of the individual models the way they human can. Ensembles also don't work if we're looking at different levels of organization, such as what we have here in this example, where we may have information coming from docking about how a chemical might interact with the estrogen receptor. We have transactivation assays to also tell us how well the chemical is not only interacting with the receptor, but how well it's actually causing that receptor to undergo transactivation and to cause the expression of genes, which is ultimately what the estrogen receptors alpha and beta do. We could have QSAR models that also are looking at just the chemical structures of ligands to predict, is this a good ligand? And then we can also have AOP Bayesian networks as well. They're taking some of the other kinds of information from other assays, bringing this in to say, okay, so are we actually getting not only estrogen receptor activation, but are we actually seeing estrogenicity? And that's really a very key point, because activation of the receptor itself is not necessarily adverse if that activation doesn't then lead to estrogenicity. And this is where an AI human hybrid intelligence team can really begin to work better. If we have humans working together with our computers, and the humans understand the strengths and the weaknesses of the computers, it's no different than, human teams, right? So teams where we have lots of humans. Generally, if you practice together, if we take the analogy of team sports, let's say soccer, if you have a lot of players who are playing together, they're training together, they're at practices together, they play games together, they begin to understand each other's strengths and weaknesses. And so now when you're on the field and you need to make a decision, you can very quickly decide, I should pass over to this person, they're in a better situation, everything is just going to work out better. Or, for this particular kind of play, this person isn't the best. Maybe I should dribble up and go over and see if I can find a different situation and how that all shakes out. So that's really the principle. But how do we get there? That becomes a very important question. So, to me, trust in the software is probably the thing that Kasparov was really able to show. That we need to not only understand how the software works, we need to understand how it makes these predictions and why it makes these predictions. And when we get that level of understanding, now we can see what these strengths and weaknesses really are. Now, someone might say, but with like a QSAR model, you have that, don't you? You have this domain of applicability. Doesn't that get you enough? Well, that domain of applicability is kind of what we would call explainable AI, which is I don't necessarily know how the black box is working, but I do know what features were used, and I can use different ways of figuring out which features were most important. And so in a black box QSAR model, yeah, I can get to explainable, but that doesn't actually help me understand when it sees a new compound. And, I mean, we can debate how we're going to actually, decide what the domain of applicability is. There's lots of debate still on what is the best way of doing that. Really, the best way forward is to know how and why this software, the AI, is making its predictions. And ultimately, if we're going to go to court, we are going to have to demonstrate that our AI is actually reliable, at least in the United States. And that's the Daubert criteria in a federal court. So under Daubert, we have to demonstrate that it is reliable and that other individuals have used this software successfully, and that it continues to make predictions that we can rely upon. One of the easiest ways for me to question its reliability is to start poking holes because you don't understand how and why it works. Then I'm going to do what we call fuzzing, which is a security technique where we just throw a bunch of random stuff at the algorithm and see when it breaks. And we can use random structures to figure out when it breaks. Now someone could say, but it's outside the domain of applicability. Again, in a court, I could argue the fact that there are all these different ways of, determining a domain of applicability. If they don't all agree, how can you tell me which one is best? And so therefore, explainable AI is not going to be sufficient here in order to determine reliability. I need to know how and why it came to these conclusions, which kind of brings me to the next point, which is black box models probably are not going to be sufficient for regulatory purposes. They might be very good at certain things. They certainly can be a lot faster to build. And they probably are much faster to build when we have lots and lots of data. We don't have that situation right now in biology and toxicology. We don't have tons of data that we're looking at. We have very small data. Biological big data is not the big data that we typically are talking about. And so for various reasons, the how and the why, it's something that is within reach for us, and something that's probably going to be very important as we go into the future, where these things are making decisions about chemical regulations, and someone ultimately is going to press back on the fact that the AI may not be reliable. One of the other points that we need to ensure is ethics. We need to make sure that the data were ethically sourced. We need to make sure that if it was data from an animal study, that the animal study was properly approved. If it was data from a human study, we need to make sure that all the privacy protections are there. Were these studies that were generated, were the studies that generated the data performed? And that becomes, again, another issue for human and animal studies as well. And do the algorithms perform well enough to avoid causing harm? That is probably the bigger ethical question, and it really gets back to performance. So what is an acceptable level of performance? What is an acceptable false positive rate? What's an acceptable false negative rate? And are we measuring the performance of these algorithms appropriately? If we have small models that are built on very small amounts of data, so less than 1,000,000 rows, let's say, then we probably really shouldn't be doing the the train validate approach, where we have a test set and a validation set, and a train set and a validation set, and we're training on the training set, and then we open up the sealed envelope and validate it to see how it performs, which is common in QSAR modeling. That's not going to work. Some people take a hybrid approach where they do cross-validation, and so they're doing cross-validation on the quote-unquote training set and then they open up the envelope, that's still not sufficient. We have various performance issues why we shouldn't be doing that. We have such a small data set. What you're doing is ultimately you're constraining that domain of applicability, right? We're constraining the examples. So what we should probably be doing, based on the best practices in the literature, really is focused on cross-validation of the entire data set and building the model using that information, using the performance from the cross-validation to justify our performance claims of the algorithm. That would certainly be more ethical than what we're currently doing. When you're splitting the data set apart and not doing a cross-validation approach, what ends up happening is there's evidence that we may be inflating the performance of the algorithm inappropriately. One of the other questions that I have coming from a statistical background is bias. Um, so we've seen a lot of literature about AI biases, especially in the um, criminal justice system. And a lot of this is being driven by the fact that the criminal justice system tends to have a preponderance of individuals of specific races who are being perhaps overly punished due to various social things that are going on. You know, and what ends up happening is when you're training AIs, artificial intelligence, on already socially biased data, you're going to create socially biased AIs. The same thing is true in our field of science. If all we're doing is training our AIs on chemicals that tend to uh, get approvals, then what we're doing is we're not training it on the chemicals that tend never to get approvals for anything because they're so toxic. And so it tends to bias what we're looking at. And if we don't have examples of these really bad chemicals that probably never should be approved, mostly because the companies kill the chemicals very early on in the development process, we end up with biased AI. It's the same thing. And it becomes harder for the AI to clearly say, this is clearly bad. Right? So that becomes an issue for companies, especially when they are looking at chemicals early in their development cycles. Typically, companies want to kill those very early on. So we need to have models that are trained for that purpose. Regulators, on the other hand, that wouldn't be as useful for regulators. So regulators probably do want AIs that are trained on chemicals that are mostly approved, and to try to identify safe doses or whatever based on those. If the data that we're using is based on human data, we definitely want to make sure that multiple populations are represented, but we need to make sure that it's balanced. We understand that unbalanced data sets do cause lots of their own problems. They tend to cause the algorithm to bias in very particular ways for the majority group that's in the algorithm. So we need to be very careful that we are using or that we're not using biased data sets in that way. Probably the one thing that gets overlooked the most is evidence of statistical bias. So this occurs when we have papers that are being published in the peer-reviewed literature with really small study sizes, and we end up with a lot of false positives. And so now, are we running into a situation where we are overly regulating chemicals based on an AI that says that this chemical is toxic, when in fact those studies were really, really poor? And so the study quality is poor going into the algorithm. The algorithm doesn't know this. The algorithm just knows, hey, this is an example, and that's what I'm going to train on. So these are things that we need to consider with respect to bias that are very, very, very important. And the last part is really trust, and trust the process. The human decision maker ultimately needs to understand how and why for the AI. And by understanding how the AI came to its decision and why it came to its or prediction, the human decision maker then can figure out where its strengths and weaknesses are. It can identify, okay, so this particular chemistry has some groups in it that this AI just simply does not do well. You wouldn't necessarily be able to figure that out through an explainable AI. You wouldn't necessarily know that certain features were being used or not used is enough, because these features are actually being used in various combinatorial ways that we typically don't test for in an explainable AI situation. And that's why knowing the how and the why becomes extremely important. And the last comment I want to make is that AI and human teams, they are like human teams, and it's important and critical that we understand the weaknesses and strengths of our teammates. And the same is true with AI. The bottom line to me is we're not going to get the human out of the regulatory process. That's just not going to happen, nor do we really want that in the near term. I do think computational models are going to be great. They're going to help us quite a bit, and there's a lot of promise there. But we need to make sure that we are teaming with our AIs. And this is a lesson that, Kasparov has taught us, but it's also being used at various other government agencies, such as different parts of DoD. The United States Air Force is doing a lot of AI human teaming trials right now in order to help intelligence operators figure out what certain things are within the airspace and to keep track of friendly versus foe, and when friend signals might become foe signals. So there's a lot of experience in other parts of the government that we should also be looking to learn from as well. And I believe there are other industries that we could also learn from. So there you go. That was Strengthen Teams, AI, Human, Hybrid Intelligence, and Defined Approaches, and Improve Risk Assessment. Thank you very much. My name is Lyle Burgoon. I'm with Raptor Pharm and Tox. Visit us at our website or send us an email if you have questions. Thank you very much.